Our talks on vector spaces continue with this video, and here we are talking about linear independence, dependence relations, and redundancy. Before now, we've had snippets of talks about linear independence, dependence, and everything. And one very good sign to know if a if uh if if a system, right, is linearly dependent is to form a matrix from them, do row echelon form. If you have any row at all where you have all zeros, then in that case you say that the system is linearly dependent. But if there are no zero rows, right, like that, like every column has a pivot, then you say that they are linearly independent. And when you have linear independence, you can actually get solutions for all parameters. But if there's linear dependence, you will you're most likely going to have infinitely many solutions. And one way to even already notice that is if you see that any of the lines in the system is a multiple of another line, so you can already guess that there's going to be linear dependence in that case. So let's go into it and see what this one holds for us. Linear independence, dependence relations, and redundancy. So this lesson covers linear combinations. Of course, for vector space, right? In talking about vector space, we talked about linear combinations. Linear independence is another thing we're going to see. Then we'll see linear dependence. Then we'll look at dependence relations. We'll look at redundancy and how to remove redundant vectors. So these ideas are fundamental in linear algebra, and I used to study vector spaces and bases, right? In the last video, we talked about vector span, which is the collection of all possible linear combinations you can have for a group of sets. Okay, now we are here again talking about linear combination as a kind of refresher. So linear combinations, if we have vectors v1, v2 up to vn as vectors, a linear combination is any vector of the form c1, v1 plus c2, v2 plus all that plus cn, vn, where c1, c2 up to cn are scalars, right? We've seen that for the longest. So if you have two or more vectors, you can actually form form as many vectors as possible with them by combining them in ways where you have different by using different scalars, scalars which are constants. So imagine this example. You have vector v1 is 1 2, vector v2 is 3 1, and you want to find 2v1 minus v2. We've done something like this like two videos before now. So you just say 2 times v1 minus 1 times v2. That's just v2 itself. So 2 times 1 2 minus 3 1. So 2 times 1 is 2, 2 times 2 is 4, minus 3 1. So 2 minus 3 is minus 1. 4 minus 1 is 3, like that. So that's just straight to the point as far as linear combinations are concerned. The next thing we talk about linear independence. Linear independence. So if we have vectors v1, v2 up to vn, they are linearly independent if the only solution to c1 v1 plus c2 v2 plus all that plus cn vn is equal to 0. If that is the only solution, without c1, c2 up to cn, so if the solution is this, is C1 equals C2 up to everything up to Cn equals 0. This is called a trivial solution. So the only solution to this equals 0, given that all the constants are 0. That is when you say vectors are linearly independent. And then this is called the trivial solution because that is bound to happen if all the constants are 0. If they multiply any vectors, you end up getting the 0 vector easily. So that's the idea of linear dependence. Now the question is, what does this really mean? If vectors are independent, then we say no vector can be written using the others. That is, no vector is a multiple of the other, right? Then each vector adds new information. So every new vector you have adds new information. So if one vector is a multiple of the other, it means that the information is basically the same, right? So, and then there's no redundancy. There's redundancy if one vector is a multiple of the other because the structure is basically the same. And that's why when we looked at the idea of span, whenever you have one vector being a multiple of another vector, at the end of the day, the span is just going to be only one for those two. Then if you have three vectors where one is two are multiples of one. So at the end of the day, they are going to have a basic structure because there's redundancy in that situation. So in that case, we say independent vectors point in different directions. Whereas, okay, we are going to see dependent vectors. Let me not get ahead of myself. Okay, here, what about the geometric interpretation? In the two-dimensional system R2, two vectors are independent if they are not parallel. If they are parallel, of course, no solution. In R3, three vectors are independent. If they are not coplanar, that is, they are not in the same plane, then in Rn, independent vectors point in different directions. They point in different directions. So an example right here that we can quickly look at. Okay, can I fit this together? So to check independence, right? Um, so you want to determine if 1, 2, and 2, 4 are independent. I can already see that they are not dependent because 2, 4 is 1, 2 is a multiple of 2, 4. 1, 2 is double of 2, 4. So I can already, even from here, if it is an objective question, you don't even have to check anything. If you have a theory question, of course, you can solve all this. But without, if it is objective, just choose the answer that says they are dependent and keep moving. They are not dependent because 1, 2 is a multiple of 2, 4. Okay, but let's go ahead for the sake of solving. So step one, you form the equation. So you add you multiply this by a constant C1, or if you like, can use A and B instead of C1 and C2. So you have C1 into 1, 2, C2 into 2, 4, and then you equate that to 0. You want to check for the independence. Then step 2, you write the system. The system will be C1, all right, C1 plus 2C2 equals 0, and then we have 2C1 plus 2 plus 4C2 equals 0. So then you can solve. So if you solve this equation now, you discover that the second equation is twice the first already. So that means that C1 is going to be equal to 2 of C2. If you pick any of these expressions, so C1 is 2 of C2, because this is the two equations. If you divide this one through by 2, they are basically the same. All right. So you can see that C1 is equal to minus 2C2. That means non-zero solutions, non-zero solution exists. So if all you got here is that the fact that C1 and C2 are both zero, in that case, you'd have said they are independent. Look, since you have non-zero solutions, of course, zero solutions exist because if C2 is zero, then C1 is also zero. That exists, but that's not the only thing that exists. If C1 is one, then C2, I mean, if C2 is 1, C1 is minus 2, like that. So you can then conclude that vectors are dependent. These vectors, 1, 2, and 2, 4 are dependent. And like I told you, once you see this from the beginning and it is an objective question, like multi-choice, just choose the fact that they are dependent or they are not independent. So that takes us to the concept of linear dependence. Linear dependence simply relates with, it's of course will be the opposite of linear independence. So you can say vectors are linearly dependent if C1 V1 plus C2 V2 plus all of that up to Cn Vn is equal to 0, has a non-zero solution. So like what you have up here now, so those vectors are linearly dependent. That's why they have non-zero solutions. That's why you have C1 equals minus 2C2. So in that case, now this is called a non-trivial solution. A zero solution is a trivial solution. A non-zero solution is called a non-trivial solution. As you have up here, right, we talked about the idea of a trivial solution because we have zero solution where C1 and C1, C2 and all that are equal and they are zero. So we talk about this now. What is the meaning then of linear dependence? So if vectors are dependent, that means at least one vector can be written using others. So there's one vector you can write using others. So like 1, 2, 2, 4. So 1, 2 can be written as 2 times 1, 2. I mean, 2, 4, yes, can be written as 2 into 1, 2. So at least one vector can be written using others. Then some vectors repeat information, right? So that vector that is a multiple of another one repeats the information, the fundamental information of the one whose multiple it is. Then there's also redundancy because there's no new information that is being added by any vector at all. So look at this example. Check if the vectors are dependent. You have 1, 0, 1, 2, 1, 3, 3, 1, 4. So what do? You set up the system C1 into 1, 0, 1, C2 into 2, 1, 3 plus C3 into 3, 1, 4 equals 0. Of course, this 0 is not just ordinary 0, it is 0 vector because it is also three-dimensional. So you could as well say 0, 0, 0 if you like, but that's the 0 vector. So in that case, now what do we have? We form the system. So this is C1 plus 2C2 plus 3C3 equals 0. And then we have C1 times 0. C1, that doesn't exist. So C2 times 1. I mean, that it's 0, so we can take it off. C2 times 1, you have C2. C3 times 1, you have C3, and that is equal to 0 too. And lastly, you have C1 plus 3C2 plus 4C3 equals 0. So from there now, we can solve the equation intuitively. From here, you can already see that C2 is equal to minus C3. And if that is the case, we can substitute minus C2. Anywhere we see C3, we can put minus, we can substitute anyhow that works for us like that. So in this case, we then have, if you then substitute, so if you substitute now, let's say in the first, in any of the cases, let's say if you substitute here, if you substitute minus C3 here for C2, so this will be minus 2C3. So 3C3 minus 2C3 will give us plus C3. That's why here we have C1 plus C3 equals 0. Then you also substitute into this place. So if you, but for here we have C3 equals C1 plus C3 equals 0. So in this case now, we can then say let C3 be 1. So if it makes C3 1, for instance, so it means that if C3 is equal to 1, then it means that C3 is 1. Automatically C2 will be minus 1. And because C3 is already 1, then it means that C1 also will be 1 minus 1 just from this system. Of course, we can also solve it totally. We can, but this is like a fast way of going about it, right? So in this case now, we have non-zero solution. That means that the system is dependent. So you have minus 1, and 1 like this. We could also, okay, I mean, we're going to talk about the matrix method in a jiffy, but I mean, okay, maybe I should solve this in my own way, right? Let me solve it in my own way so you can understand the process in case that still looks somehow to you. So check if the vectors are dependent. That's going to see the matrix style. So thankfully, I found that I can just copy and paste on the other page, so I don't have to keep coming back here every time when I go to the worksheet. So I just come to the worksheet now, okay, and I open this up. So we want to check if these three vectors are dependent. So check if these three vectors are dependent. So if you like, you can have C1, C2, C3 was what we used there. So you could actually say A into, so you could say A into 1, 0, 1, okay, plus B into 2, 1, 3, plus C into 3, 1, and 4. And that is equal to the zero vector 0, 0, or you can just say 0, 0, 0 if you like. So that means you have A, 0, A, right, plus 2B, 2BB, 3B, plus 3C, plus, comma C, comma 4C equals 0, 0, 0. Okay? So now from here, we see that we can form three equations. So A, 2B, 3C. So A plus 2B plus 3C, okay, is equal to 0. That's the first one. And the second one, we have 0 plus B plus C. So that is B plus C, because the first one is 0. That is equal to another 0. Then next, we have A plus 3B plus 4C. So A plus 3B plus 4C equals 0. So we can solve this in different ways. But since this one is looking very simple, so we can just pick on it. So let's call this equation 1, call this 2, and call this 3. So we can say that from equation 1, uh, B plus C equals 0. That means that B is equal to minus C. So you can call this equation 4 if you like. So you can then substitute or put minus C for B, put minus C for B in equation 1. So what does equation 1 say? A plus 2B plus 3C is 0. A plus 2B plus 3C is equal to 0. But now we know B is minus C. So we have A plus 2 into minus C plus 3C is equal to 0. So that means that A minus 2C plus 3C is equal to 0. So that means that A plus 3C minus 2C is C. So A plus C is equal to 0. So we have another equation right here. Call that equation 5. Okay? Call that equation 5. Or maybe I should leave this one alone, right? And call this equation 4 now. Now, so this is A plus C. So another thing you can do again is you can do the same substitution in equation 3 because you got this substitution from 2. So you can also still say that. You can say put minus C for B in equation 3 again. So equation 3 is A plus 3B plus 4C. A plus 3B plus 4C is equal to 0. So we have A plus 3 into minus C plus 4C is equal to 0. Okay, now I guess what's happening here. So you have A minus 3C plus 4C equals 0. Again, A plus C is equal to 0. Okay. Now, since A plus C is equal to 0 now, so you can see that we are going to have exact solutions like that. So we are most likely going to have infinitely many solutions. So at this point, now you see these expressions are basically the same. This is like equation 5, but equation 4 and equation 5 are the same. So at this point, you have to look for another way to go about it. So you can just start by assigning, you can just say let C be equal to 1, because now you cannot get an exact solution, but you can see that they are related somehow. So let C be equal to 1. So if C is equal to 1, what does that tell us? So we can say from this equation now, from B equals minus C, from B equals minus C, we have that B is equal to minus 1. Okay, so we have C is 1, we have B equals minus 1. Now that we have these two, it's now easy to find A. We are looking for A. So from 4 or 5, okay, from from 4, from 4 and 5, which are basically the same. So we now have that A plus C is equal to 0. So we have A plus C equals 0. But we already know C to be 1. So we have A plus 1 equals 0. That means A is equal to minus 1. Okay? So, and that's a possible solution, because you could as well just say C is equal to 2, and then you get all the other ones like that. So you can say, so A, B, C is equal to um minus 1, minus 1, 1, like that. So that's a non-zero solution. So if you had got a zero solution, you would have said that those vectors are linearly independent. Because of what we have here now, you can say because we have non-zero solution, then we have the vectors are linearly dependent like this. Okay. And of course, that's why we have the possibility of having infinitely many solutions. Because if I had set if I had put C to be 2, would have got solutions too. So those vectors are dependent. Now we have a very a nice way of taking care of linear dependence and linear independence, and that's the matrix method for independence, right? So you can place vectors as columns in a matrix. So if you have vectors v1 up to vn, you can place them in vector A in a matrix A, which is v1, v2, vn. So each vector is going to form a column in this vector A. Then you can solve for AC equals 0 by row reduction. So if you have only trivial solution, that will be independent. If you have free variables, that will be dependent. So in this case, now that means after when you do the row echelon form, if there are some columns without pivots, or in essence, if there's any row that is all, if you have a zero row, automatically that is talking about linear dependence, right? So look at this now. Check the check independence of 1, 1, and 1 minus 1. So the matrix is 1, 1, 1 minus 1. So of course, you can also use the determinant method. If you find the determinant of this, 1 times minus 1 is minus 1, minus 1 times 1, 1. So you have minus 2. Minus 2 is not equal to 0. So therefore, the vectors are independent. Or if you do the row echelon form, so okay, maybe I should do the row echelon form since that's what we mentioned. So you have 1, 1, 1 minus 1, right? So you have 1, 1, 1 minus 1. These are the two vectors. This is vector v1 and this is vector v2. So this is row 1 and this is row 2. All right. So we need this to be 0 first of all. So row 1 remains. We have 1, 1. Then row 2 now. The new row 2 is just going to be the old row 2 minus the old row 1. That is 1 minus 1. You have 0. Then minus 1 minus 1. That's minus 2. The next thing we want to do is to, okay, well, I mean, even with this alone, we already see that the two rows have a pivot. So the two columns, this column has this pivot, this column has this other pivot, basically. So they are, yeah, linearly linearly independent. Okay, that's another way to look at it. So you can look for the determinant. If the determinant is 0, they are linearly dependent. If the determinant is not 0, they are linearly independent. Another thing is you do the row echelon form. If you don't have a 0 row at the end of by the time you do the row echelon form, then they are also linearly independent. If there's a 0 row, they are linearly dependent. So you have different ways to check these things out. So we go on to talk about dependence relations. So a dependence relation is an equation C1V1 plus C2V2 plus all that up to plus CNVN equals 0, where at least one CI is 0. So if you have any CI to be 0 here, in that case, that's what you call a dependence relation. It shows how vectors are related with themselves. So imagine these vectors now. vectors 1, 2, 2, 4, 3, 6. You can already see linear dependence because this one is twice this. 3, 6 is twice 1, 2, right? So you can see here that 2, 4 is 2 times 1, 2. 3, 6 is 3 times 1, 2. So the relation is such that you have 2 times V1 minus V2 equals 0, right? Uh, that is, you have 2V1 here minus V2 is 0 because V2 is 2, 4, right? And then we also know that 3V1. So you see 2 times V 2 times V1 minus V2 will give us 0, whereas 3 times V1 minus V3 will also give us 0. Because 3 times 1, 3, 1, 2 is the same thing as 3, 6. So you get 0. So we have those relations like that. So that's how you can find dependence relation for an equation. Okay. Now, finding dependence relations, right? Another, you can go for these steps. Put vectors in a matrix, then solve AC equals 0, then find non-zero solution and write equation. So an example for that would be this now. So we're looking for dependence relation for 1, 0, 2, 1, 3, 1. So you have 1, 0, 2, 1, 3, 1 like this. Then you form the system. The system is basically C1 plus 2C based on this now. C1 plus 2C2 plus 3C3. And for the next line, you have C1 is not there because it's multiplied by 0. C2 plus C3 equals 0. So from here now, you can say, you know that C2 is equal to minus C3, right? So, and by the time you substitute C3 here, you have minus 2C3 plus this. So you have C1 plus C3 equals 0. And at this point now, you now have to do the same substitution thing. So if you let this C3 be 0, or C3 be 1 rather, it means that C2 will be minus 1. And based on this now, C1 plus 1 is 0. So that means that C1 is also minus 1, just like what we did before. And in this case now, the relation will just follow this thing you have here. Minus V1 minus V2 plus V3 equals 0. Of course, there are other things you could have done. You could have said let C3 be minus 1. In that case, now if you multiply through by minus, this would have been 1, 1, minus 1. So this would be V1 plus V2 minus V3 equals 0. So that's still the same relation depending on whatever you choose to do. That's the fundamental one. So we go for redundancy. So they are all still related to the whole idea of dependence and independence. So redundancy, a vector is redundant if it can be written using other vectors. Like 2, 4 is redundant because it can be written, if you have 2, 4 and 1, 2, 2, 4 is redundant because 2, 4 can be written as 2 times 1, 2, right? So removing it does not change the span. So if you have a set of vectors, you have 1, 2, you have 2, 4, and you have 3, 6. If you remove 2, 4, and 3, 6, you wouldn't have done anything wrong because the 1, 2 is essentially the same as 2, 4, and 3, 6. So in that case, you say dependent sets always contain redundant vectors, right? They always contain one is a multiple of the other most of the times or more. One or more is a multiple of another one if they are dependent. So example, you have these vectors 1, 0, 0, 1, and 1, 1. So we see that. So from here, you see that 1, 1 is the same thing as when you add 1, 0 plus 0, 1. So in this case, this 1, 1 is useless, right? Because in essence, the addition of these two is going to give you this. So the third vector 1, 1 is redundant. So you can actually remove it because it is not adding any new information to the system. So how do you remove redundancy? The method, you can form the matrix, you do the row reduction, you find pivot columns, you keep the pivot vectors and remove others. Okay. For instance, imagine this matrix. You have these vectors 1, 2, 2, 4, 3, 1, right? Of course, you can see 2, 4 is a multiple of 1, 2 already. So it means 2, 4 is redundant. So you could as well just end the game. Like from here, you can cross out this 2, 4 and just leave 1, 2, and 3, 1. So these ones are not redundant in that case. But let's follow the rules, right? So you have matrix A 1, 2, 2, 4, 3, 1. And when you row reduce, of course, row reduction, you can keep this one. And then if you do the row reduction, 2 minus 2 times 1, that's 0. 4 minus 2 times 2, that's another 0. 1 minus 2 times 3, that's 1 minus 6, which is minus 5. By the time you're done, this column has a pivot. This second column doesn't have a pivot, but the third one has a pivot. This third one has a pivot, right? At the end of the day, you see the middle column is useless. So at the end of the day, you remove 2, 4, which I already knew you could remove from day one. So you are left with 1, 2, 3, 1, right? So you see that the pivot columns are 1 and 3. So, and then you can keep the original 1, 2, 3, 1. So because 2, 4, you remove 2, 4 because it's not adding any new thing because it is essentially 1, 2, right? So we have some important theorems that go with this whole idea of redundancy and all that. Okay, wow, this is so long. Okay. So we have this now. In Rn, in n-dimensional real number system, any set containing more than n vectors is linearly dependent. So any set containing more than n vectors is linearly dependent. Then this is because Rn has only n independent directions. So at least one vector must be expressible as a combination of the others. Therefore, it is impossible to have more than n linearly independent vectors in Rn. Okay. Then we also have sets containing the zero vector. Any set of vectors that includes the zero vector is linearly dependent, right? Because you have a zero part there that is going to be that can be excluded. So it's more like having a zero row in echelon form. So this is because the zero vector can always be written as a scalar multiple of any vector. So if you have a zero vector, right, it can be written as 0 times 4, 3 plus 0 times 3, 1, everything is still zero at the end of the day. This is because the zero vector can always be written as a scalar multiple of any vector and it contributes no new direction to the set. As a result, its presence creates a non-trivial solution in the linear combination equation. Another theorem we have is that of repeated vectors. So any set that contains repeated or identical vectors is linearly dependent, like that case of 1, 2, 2, 4, 3, 6. So 2, 4, and 3, 6 are simply repeating 1, 2. They are essentially 1, 2, so they are not, they make the set, the vectors linearly dependent. If two vectors in a set are the same, one can be written as a scalar multiple of the other. So this leads to a non-trivial linear combination equal to 0, which makes the set dependent. Okay, so we have important theorems surrounding more vectors than dimension, sets containing the zero vector, and repeated vectors. So in summary, we have this that a linear combination is more like a weighted sum of vectors because if you have vectors v1, v2 up to vn, then the linear combination is like you're weighing there by multiplying with constants. So c1 v1 plus c2 v2 plus c3 v3 up to cn vn. Then when you talk about independence, right? Vectors are independent because because the linear combination has a only trivial solution. They are dependent if they have non-zero solution. Then for dependence relations, this shows dependence. Redundant, it means it can be removed. So you have 1, 2, 2, 4, 3, 6. So you can remove 2, 4, and 3, 6 because they basically just duplicate 1, 2. Then you have bases, which are independent and they are independent. The meaning is that they are independent and they span. Okay, well, you may be wondering what is this span thing about. In the next video, we're talking about basis and dimension, so you'll understand better the idea of basis. So we have some practice problems here, like this. Okay, determine whether the vectors are linearly independent. Of course, I can already see that they are linearly independent because they are linearly independent because 1, 2, and 3, 4, you cannot express any 3, 4 as a multiple of 1, 2. So if it was 3, 6, we would have been able to do that, right? Determine whether the vectors are linearly independent. This is linearly dependent because 2, 4 can be written as a multiple of 1, 2. Check if the vectors are linearly independent in R3. Okay, they are linearly independent in R3. And then like we did before, you can do the row echelon. There are many approaches, so you just choose which one you want to use. So you can set them up and do. I think I saw this kind of question previously. So you do put them in echelon form and if you have any zero row, then they are linearly dependent. If there's no zero row, they are linearly independent. Find a dependence relation among the vectors. So if you add this to now, you have 1, 3, 4. So this third vector is useless because 1, 2 plus 2, 3 will give you 3, 4. So by combining this, you have this. So this is not adding any new information. Then find a dependence relation among the vectors. Oh, yeah. Oh, we are looking for dependence relation, right? So it's more like you have okay, I mean you can do the same procedure like before, right? You have 1, 1, 2, 3, 3, 4, and then you do it to the list and then you write a relationship as much as it can as possible. Find a dependence relation among these vectors, same story. So now we have determine whether the following set is dependent on linearly or independent. This is a for okay, I mean you can form the matrix, do the row echelon thing. If there's a zero vector, they are linearly dependent. If there's no zero vector, they are linearly independent. Identify the redundant vector, if any. 2, 4 is redundant, definitely, because it's a multiple of 1, 2. So remove redundancy and find the basis for the span. Okay, so uh you can remove the redundancy if there's any. Okay, 2, 2 duplicates 1, 1. So 2, 2 can be gone. And then apart from that, 1, 0 plus 1, 1, 0, 1. 1, 1 can also be gone because 1, 0 plus 1, 0, 1 can give you this. So you just have the first two columns. so you can then do the span thing. Then, of course, if you can find the basis. We'll talk about finding basis in the next video, like I said. Determine whether the following vectors are independent. You know the trick. Well, in this case now, they are linearly dependent. You don't even have to go too far. But if you want to do the matrix thing, so just do your matrix and reduce. And you can see 246 is the multiple of this, 369 is the multiple of this. So these are two are redundant. So they are linearly dependent, right? 10, find all values of k for which the vectors are dependent. Okay, we want to find all values of k for which all these vectors are dependent. So all values of k here. So it's possible from here now. It means we just need to say, this is 1k. For them to be linearly dependent, this expression has to be a multiple of this. So, and we can see it's clearly 2. So 2 times 1. So we have 2, 1, 2, 1, you know. Uh, so then we can say that so from here we just multiply this by 2. So you have 2 comma 2k equals 4. So 4 2, if you multiply this by 2 now, so because already this one is a multiple, it's 2 times 1. So this 2 is 2 times 1. So 2 times 1, 2 times k. So you have 2 comma k. So 2 is 2, then 2k is equal to 4. So k is also equal to 2. So that's the value of k that makes the vector dependent. Okay, so with that, we come to the end of this video. Let me know how helpful this is for you. And if there's something else you let me try out, feel very free to let me know. Don't forget to try your hands on the questions. Here I have 1 to 5, and here I have 6 to 10. If you have subscribed already, I must thank you very much for doing that. If you have not, what are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can as well become a member of the channel, and that comes with some special privileges, like you getting to see some videos alone as a member, or you see the videos first before others see them, or other options would be you may get some of my PDF notes for teaching some of these things. We can also hang out together. I can explain an idea for you that may be not so clear. All right. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.